Hello and welcome everyone to the security track of today's Rambus Design Summit. You will be able to attend a number of interesting security sessions today, including a hardware security Ask Me Anything session that will be attended by Rambus security product managers. I will be kicking off for today. Please note that the PDF for each session will be made available to attendees. My name is Bart Stevens. I'm responsible for product marketing in the security IP business unit at Rambus. At Rambus, our secure silicon IP and provisioning products protect over 9 billion customer devices annually. During the next 30 minutes, we will look at the solutions for securing data center, AI, and ML workloads. We will progress through this session in 3 steps. First, I will address what problems are we solving by securing machine learning workloads. I will touch upon traditional security requirements, as well as expanding these requirements to provide a full security solution. Second, how do we architect and implement the security solutions? For example, by anchoring security in your hardware. And third, walk through a couple of use cases, always helpful, explaining how these security solutions look like when implemented on AI accelerator blades, for example. Data centers handle large amount of machine learning training workloads for their independent customers. The vast amount of workloads call for efficient processing. To handle these workloads, dedicated AI processing hardware has appeared on the market. These dedicated architectures are offered as pluggable blades and implement the latest state-of-the-art neural processing architectures. Many new entries in the marketplace have released such implementation in recent years. The actual workloads to be handled, being it inference models, inference algorithms, training models, training datasets, they are considered valuable intellectual property. Since these valuable assets are handed off to data centers for processing on shared hardware resources, these assets need a high level of protection. Now, suppliers of AI acceleration services must provide assurances they are able to protect their customers' valuable assets. Like in every segment where security is paramount, a secure by design approach needs to be followed. Implementation of security cannot be an afterthought, as that approach has proven itself to be resulting in flawed implementations over and over again. Various aspects of security need to be taken into account in the planning and in the architecture phase. It's good to know that proven security and cryptographic solutions exist that can handle the high throughput requirements in this AI and ML segment. When securing an electronic system such as an AI accelerator blade, we are addressing these 4 security fundamentals shown here. Confidentiality, which is preventing access to information by entities you do not wish to share it with. Confidentiality is achieved by using robust encryption algorithm implementations together with secure key management techniques. I'll discuss later on that encryption will need to happen in multiple subsystems in the architecture. Second, integrity, which is making sure the system or its data has not been modified to ensure the system works as intended. This can be about the data being worked on or transported, the inference models, or the actual system and algorithms handling the data. Third, authenticity, which is making sure something is genuine and can be trusted to come from the intended source. These 2 aspects, integrity and authenticity, can be achieved by using robust integrity and authentication algorithms and protocols, again, with proper key and identity management. The last pillar here addresses availability, which is making sure something is available and can be used when needed. High availability is key, especially in data centers. Availability assurance can be achieved by implementing trust in a design, starting from running trusted hardware and booting and executing trusted software to implementing anti-tamper mechanisms, for example. Please note that all of these security aspects actually also apply when processing AI and ML workloads on edge devices, so not necessarily only in the data center. Let's look at machine learning assets at risk. In refreshing our memory about the AI assets at risk, when handled by data centers, edge nodes, or endpoints, often the threats to AI systems are to maliciously influence them into making alternate decisions. This could be done by input attacks or by poisoning attacks, for example. Other threats are to steal valuable assets like inference algorithms and models, data sets and training sets. Understanding algorithms and models by an attacker makes influencing the outcome easier to achieve. The attacks can occur at multiple layers. Attacks can target software, firmware, hardware, or all of them. They can be invasive, they can be non-invasive. They can enter across the network, enter through an edge, or they can directly target endpoints. It will be critical to safeguard all data, algorithms, and models handled by an AI ecosystem. With AI-powered devices flying our skies, driving our roads, and protecting our neighborhoods, an attack that compromises the operation of these devices can threaten privacy, property, and personal safety. So, to protect these assets at risk, the various threats like denial of use, misuse, device and data tampering, theft of assets, such as the mentioned inference and training models and datasets, need to be handled by appropriate security countermeasures. Let's look at the various components on a typical AI accelerator blade shown here. The heart of the system is often provided by powerful accelerator chips, ranging from a handful to a large array of dedicated AI processing units, each with their own pool of memory attached. They process as many tasks on as much data as possible with the shortest latency. Security is not the primary goal. It's quickly overlooked or seen as overhead at the least. Not always present, but typically seen on blades is a gateway CPU, with its dedicated flash and DDR, and with the task to manage models and assets, and to program and control the accelerators. Finally, here is the connection to the fabric, offered by high-speed network or PCI Express interfaces. Some blades also have proprietary inter-blade links. Let's dive into outlining the security requirements next. Like in any system these days, AI accelerators need to follow security requirements that at a minimum authenticate and protect the blade itself. For authentication, a blade would need to get an identification number that not necessarily needs to be kept secret, just needs to be unique and immutable. This ID is typically injected in a so-called personalization phase, which for example can happen at final assembly or during test. Note that there can be more than one ID, one for each chip, one for the blade or the appliance itself. Provisioning and key management is done in later phases, during enrollment, for example. In provisioning, the services, key materials, and certificates for such services are generated and securely loaded into the system. Protecting the blade itself is all about trusting the appliance, which builds upon the previously mentioned device ID, as well as provisioned keys and certificates. Using these assets, a trusted or secure boot chain can be established, where a master CPU, this could again be the gateway CPU here, validates software images for their integrity and authenticity using strong digital signature schemes before allowing the system to boot. Even software confidentiality, something which is important to protect intellectual property, can be guaranteed by using such image decryption. All these protections can be managed by the gateway CPU, for example, or by the accelerator units themselves, or both in tandem. This differs per implementation. Elevating the security requirements for protecting the blade one more level would, for example, add tamper detection and memory protection. Where the earlier traditional requirements would handle the static assets, such as firmwares and keys, these new techniques ensure that a blade can keep functioning in a trusted manner after being deployed. The most elaborate secure boot schemes become void if an attacker is able to glitch the final go or no-go decision gate in a secure boot process. Mechanisms to detect tampering, like bus probing, clock and voltage glitching, help protect against bypassing the secure boot process. In addition, the ability to service the blades in the field in a secure way is very valuable. Secure firmware updates, as well as the ability to be able to debug the system in a secure way, are becoming table stakes. Where the previous slides discussed protecting the equipment itself, there are additional specific security requirements for AI acceleration. One of these is protecting all valuable assets. Secure AI implementations are required to prevent the extraction or stealing of inference algorithms, of models and parameters, training algorithms, and training sets. This would also mean the prevention of unintended replacement of these assets with malicious algorithms or data sets. Protection against this would avoid poisoning the system to alter the inference results, causing misclassification. Also important, data privacy regulations such as HIPAA in the US and GDPR in Europe should not be violated by your equipment. When the AI blades are installed in public cloud servers, they tend to be assigned to handling workloads of various tenants dynamically. The ability to switch between different users or tenants in a secure way avoids contamination and protects your customers' assets. Finally, security should also be present to avoid misusing a system, to ensure proper billing of services, and prevent unethical use such as racial profiling. This table is placed here for some bedtime reading. It provides a summary of the various threats and impacts of these security threats. As mentioned before, a robust security architecture can and should handle the protection against these threats. Again, you can download this as a PDF later on, so I'll not read aloud all these items here. Let's move to implementation aspects of security. Let me avoid reinventing the wheel by referring to the 7 properties of highly secure devices that have been published by our colleagues at Microsoft Research. These 7 properties are a hardware root of trust, defense in depth, a small trusted computing base, dynamic compartments, password-less authentication, error reporting, and renewable security. Each of these properties are described in this paper in detail, accompanied with questions to test each property. I invite you to study this white paper to get familiar with these properties. Not all of these properties would apply immediately to a piece of silicon, but they certainly apply to a complete system. I will focus more in the upcoming slides on one very important property, which is the first one in the table, the hardware root of trust, which is there to ensure hardware protection of device identity and integrity. Another one, the small trusted computing base, defines the storage of private key materials in a hardware-protected vault and refers to the mentioned hardware root of trust. To meet the mentioned fundamental security requirements, we need to ensure that data is secured at rest when it resides within a device such as a server, that it's secured when it's in motion, when this data is being exchanged between devices or components, and it's secured when in use, when moved in and out of external memory. Methodologies such as encryption are fundamental to protecting data at rest, in motion, and in use. The underlying algorithms for all of these are typically the same. They are built on well-established and crypto-analyzed cipher and hash algorithms. The difference is that for data in motion, the throughput requirements are extremely high. For data in use, the same holds, added with very low latency requirements. Used key materials are typically ephemeral in data at rest, or in data in motion and data in use, as their protocols typically work with short-lived session keys. On the other hand, data at rest typically allow adversaries to have more time to analyze and attack such systems, as the assets are often static and stored onto the devices. That is why you see more protection mechanisms such as secure provisioning, anti-tampering, and side channel protection in the data at rest column. Data at rest protects assets such as keys and OTP, firmware, device identities, and device settings. As we look into the complete architecture for AI security, beyond the AI accelerators only, we will implement according to the security by design principle. Here again, the 7 properties of highly secure devices apply. There are 4 components used in this approach. First, the hardware root of trust can be built into the chips powering the devices in the core, edge, and endpoints. Second, keys and other secure data can be provisioned in these chips at time of manufacturing. Third, data traffic moving across the, for example, 5G network can be secured with security protocol engines. Like the hardware root of trust, these are built into the communication chips in the various devices. Using key management services, the chips and devices provisioned with keys can be securely managed via the cloud during their entire device lifecycle. And fourth, data stored in off-chip DDR memory modules can be protected by injecting fast, low-latency inline memory encryption decryption modules. Here we see again the typical AI blade or appliance block diagram with the gateway CPU, the accelerators, the DDR or GDDR modules, and the communication link, again being PCIe or some other high-speed network link. Let's inject the data in motion and induce security modules mentioned in the previous slide. The network or PCIe link to the fabric should be protected by inserting a high-throughput Layer 2 or Layer 3 protocol-aware security packet engine. Such a packet engine has security protocol awareness and require little support from the CPU, apart from some security association management. In later presentations today, you will get more in-depth overviews of network encryption. The contents of the gateway CPU DDR and local AI accelerator DDR can be protected by an inline memory encryption engine. The protocols for this encryption are typically based on high-throughput AES GCM with robust side channel protection. Keys for the session can be generated locally. One can argue if memory encryption is also protecting data at rest, which is true, but the nature of the implementation and the fact that it protects data that goes off-chip into DDR modules places this in the data in use category. Regardless, protection is highly recommended. If a dedicated blade-to-blade communication channel exists, it can be protected by high-throughput AES GCM or AES XTS-based link encryption accelerators, exchanging models and datasets between blades without having to go over backplanes, all in service of extreme processing capabilities. Key management can be handled by the gateway CPU and its embedded root of trust. Solutions for all these exist in the form of dedicated, efficient accelerator IP cores that can be used in any CMOS node. There are some links to these products on the Rambus website. Let's move on to the data at rest category. As mentioned earlier, data at rest protects assets such as keys and OTP firmware, device identities, and device settings. The vital component in protecting the device and the data at rest is the hardware root of trust. A hardware root of trust can be a discrete component on a blade. Typical examples of such discrete components are a trusted platform module, the TPM, or a secure element chip. They could be integrated in the baseboard management controller, but this is not common. Higher level of security integration for data at rest protection can be achieved by embedding the root of trust into the CPU and NPUs themselves. This allows for tight integration into the chips, lowering costs, lowering risks. The tight integration allows for total control over the secure boot process, as well as all the other important data at rest use cases, such as personalization, provisioning, firmware upgrade management, secure debug, secure feature enablement, authentication, attestation, runtime integrity, asset encryption, data privacy, and last but not least, secure key storage. This would also include the handling of protected training models and inference algorithms. This very rudimentary block diagram shows the most important components of such a hardware root of trust that can be embedded in ASIC or FPGA designs. A robust root of trust is purpose-built for security with operations siloed from main processing. In tandem with a layered security model, it provides a level of security provided by hardware with the added flexibility of secure software. This layered security model can, for example, shield all cryptographic processing and key handling from the security CPU. In this case, even the security software would not be able to access key materials nor misuse it. The root of trust should have a full feature set for executing complex crypto algorithms and security protocols. Think of a certified random bit generator, one or more symmetric cipher accelerator cores, an asymmetric or public key infrastructure accelerator core, an integrity core, the so-called hash and HMAC, and secure key derivation cores to prevent overusing immutable keys. These root of trusts should implement strong anti-tamper features to guard against side channel attacks, like differential power analysis and fault injection attacks. Depending on the required flexibility and security application needs, the root of trust implementations can range from state machine-based to secure core processor-based. Finally, root of trust implementations should be certified against security standards. In this section, I will look into a couple of security use cases. One of the major security use cases is ensuring the availability of the accelerators themselves. An adversary can tamper with accelerator hardware to deny or disrupt usage or bypass its security measures. The root of trust core embedded in the various ASICs can monitor system status and memory contents and detect tampering activity independently to the applications and the CPUs or MPUs. The root of trust can also detect security attacks like fault injection. A couple of steps of such a monitoring process are depicted here. The root of trust in the gateway CPU monitors test and debug logic, hardware configurations, and other hardware statuses of the SoCs. The root of trust in the accelerator monitors ML accelerator operation. The root of trust periodically hashes known embedded SRAM state to detect tampering. It can periodically hash invariant flash data. Internal logic inside the root of trust detects physical attacks to the system. And a security protocol engine can monitor network traffic. The security applications running inside the secure boundary of the root of trust determine how to act upon a detected anomaly. This could be as simple as logging, or as far as restarting the system, or even disabling the system upon further inspection. This is determined by how the root of trust security application is authored. Earlier, we identified the inference and training models as valuable assets that require protection. While in use or while loaded into the AI accelerators, these models can be intercepted, replaced, or altered. Upon completion of training, the resulting inference models should be best stored in encrypted form and decrypted dynamically upon use. A couple of steps of such a process are depicted here. The signed encrypted inference model is stored in an off-chip flash module. The root of trust module reads the inference models from flash, decrypts them, and hashes the decrypted data. The root of trust verifies the signature and compares hashes. Only if the hashes match, the model will be loaded into the accelerator. Alternatively, if each accelerator has its own flash, the local root of trust can handle this. The root of trust would require capable encryption, hashing, and digital signature verification capabilities. When a complete AI ecosystem operates in inference mode, an adversary can target to tamper with the inference process or the inference results. Protecting the inference results can be done using a secure channel similar to that used to protect input data integrity. A couple of steps of such a process are depicted here. The host module communicates with the edge devices over the network. There will be mutual authentication using pre-provisioned keys and identities. After establishing a secure communication channel, the root of trust in the edge device manages passing of inference results to the servers. Once loaded in the AI accelerator, there is an integrity check of the inference results before committing them. Okay, let's bring this presentation to a conclusion. In summary, dedicated new neural processing architectures appear on data center blades, where higher value of inference model and training data and increased network vulnerabilities increase risks and need for security. Deployment of well-architected multi-layer security protects data at rest, data in motion, and data in use, where security anchored in hardware provides the highest level of protection and performance. Hardware root of trust and security protocol accelerators embedded in an AI ML accelerator or in an edge device protect the physical hardware, inference model training data, and inference results from a broad range of threats. I hope this presentation was informational. I will conclude showing this last overview graph outlining the Rambus security product offering. In blue are secure silicon IP products, the secure devices are listed, and in green are secure provisioning products for securing the supply chain are listed. Feel free to contact us on any inquiry of this subject, and please browse rambus.com/security. Have a nice day, and thank you for your time and attention.